All right, then welcome back everybody to this afternoon. Thank you very much for being back on time, so we can actually start the next talk without deviation. But of course, we have to introduce some deviations today. So the session of this afternoon is actually swapped with a session of tomorrow. So there are two parts on process enhancement. So this afternoon, Dirk Valand will present his work, was originally scheduled for tomorrow, and the presentation of this afternoon is moved to tomorrow. This has to do, and it will be online, because of two positive COVID tests of both the authors that were supposed to present. So they are doing this online. But the first in the afternoon, first session of this afternoon is fortunately live and without any deviations. So I'm welcoming Jochen de Weert here. So we've been talking about process mining now for 1.5 days, with the starting point always being an event log. And especially those of you who've ever seen real systems, they know that event logs are not something that you get out of a computer easily. So Jochen is going to help us show us how you actually get to event logs and event data. So Jochen, go ahead.
Is this working? Yeah? All right, thanks. Thank you, Barwen, for the introduction. So yes, indeed, I think for the past 1.5 days, you have been climbing a mountain, right? And you've been looking in quite a lot of difficult topics. Marking equations, alpha mining, declarative mining, etc. And so we're actually on top of the mountain, and now we put all on a blindfold, we walk towards the edge of the cliff and we jump, basically. That's a little bit what you can expect from this presentation, because data pre-processing is a topic in process mining which is, especially by academics, often disregarded, kind of like, let's assume that it's there and then we work with it. But there is actually quite a lot of things to say about it. So in this doctoral school, or in this summer school, the idea was to, for me to basically look at a more academic perspective on pre-processing, and then Rafael and Julian to complement it with a very practical perspective in their session. That's still something that you will get tomorrow. So yeah, this is what you can expect from my side. So yeah, maybe very shortly, I work in Leuven, obtained my PhD in business economics. So I'm not a real computer scientist, although we do quite a lot of computer science alike research. I have a research team, currently 8 PhD students, and roughly half of them actually work in process mining. I also have other PhDs in regular data science problems, or working on regular data science problems. But maybe Jari or Hans or Björn or Yannis, you might have met them already in maybe some of the academic conferences. All right, what did I prepare for today? Well, an introduction. Where do we source data? What are the complexities with sourcing event data? That's what I will introduce, or what I will do for introduction. We looked into the structure and extraction techniques, event correlation abstraction as an important topic. Then data quality, as you've seen on the introductory slide. I prepared this session together with Mo Win from Queensland University of Technology. She's actually someone with a lot of expertise and a lot of research projects recently on the topic of data quality, so I will also introduce you to that type of work. And then I will conclude with some more exotic things like IoT, like trace clustering, and like autoencoders, but that's something that will come at the end. If you have any questions, of course, we have questions at the end, but you can definitely also interrupt me. Let me start with this. This is from a tweet from Jorge Munoz Gama. Maybe you know him. Funny character, great researcher in our field. And he is a very active Twitter person. And this is of just a few weeks ago. So the POC took 4 months, 3 months for data collection, 1 for analysis. Beware of log. Yeah, that's exactly a picture summarizing the problem in process mining, especially for practitioners, right? So this is something that we should be aware of, I think, also more in research, and that we should think about certain problems with where to source the data and the complexities that come with not only sourcing the data, but also understanding it, assessing quality, rectifying quality, etc. This is something that usually in most projects take 70–80% of the time of most in most projects, especially for those projects where the organizational maturity to apply process mining is still at a lower level. Maybe to ask a quick question, anyone who knows how many tables there are in SAP for or S4 for HANA? Yeah? Yeah, it's actually, I read that it was 800,000. Yes, so but that already puts it a little bit into perspective, right? So you have a table that describes all the tables, and that usually has like 800,000 rows. So imagine that you as a, whatever, process analyst, data scientist, starts working within SAP to try to extract your data. That's the starting point, roughly 800,000 tables. That's not like something that is easily digestible, let's say, right? So event log preparation is key in any process mining project, but because it takes a lot of time, because there's lots of complexities. But in research, actually, research is quite limited in that sense. We haven't been looked at the whole process comprehensively, let's say. We have been focusing on a couple of topics, and I will introduce them here. Event abstraction is one of them. Data quality, also very recently, has gained a lot of traction, but to be honest, it's quite fragmented, right? So it's still quite fragmented, and I don't think I can claim that there are very good end-to-end solutions to cover the entire problem of like how to get to quality event data. That's also what you see in frameworks that describe methodologies for conducting a project. This is the PM² model, which you might know. Also there, you can see that there is an emphasis on extraction and data pre-processing. And if you look at the methodology and at papers that apply the methodology, you see that sometimes they have some explanations about it, but the core things that is being researched is typically not in that stage. 90% of the research, more than that, in process mining is typically in the fourth, in the fifth stage, but not really at the level of data pre-processing and extraction. All right, let's move a little bit to like what is this event data? We already got that introduction, so I will keep it short, but there is a few extra things I want to say, and I would like to couple it to the task of extracting data. So this is something that you should know by now, right? And I know in the regular program this would have been still be very easy. Dirk, who comes next, might actually put you upside down and start shaking with you in terms of my assumption that typically we have a case ID, an activity name, and a timestamp. Those are the three essential requirements that we need to do process mining, or at least that's what everyone says. And I also still claim this. So in basic form, we are looking for a data set that has those three essential requirements: a case ID, an activity name, and a timestamp, so that we understand the order of the events, right? I will not spend too much more detail on this. I think this is something that you know, and it's not too complex to understand. What we do see is that in many process mining cases, people, especially in practice, they are not only using these three essential fields in a data set, right? For a lot of process mining analysis, for filtering purposes, just to understand like the cases that you have, that you want to analyze, you typically use a lot of additional variables that come with traces or that come with events. So typically we make a distinction in process mining between case attributes. Those are basically static attributes that do not change, like in my small example, you had plant, country, city. Those are things that, like for one process instance, these variables stay the same, they keep the same value. We also have event attributes in an event log, or we can have event attributes in an event log. And those are typically features that are particular for a particular event, and they can also change over time, at least insofar that you record these events in a case, or record these event attributes for multiple types of events in a case. So usage typically for filtering purposes, contextual information is also often a reason to include these additional data attributes in your analysis. And then we have a large set of dedicated mining techniques. For instance, techniques focusing on a resource perspective, on costs, also in predictive process monitoring, of course, also there you see that these additional data attributes, their importance increases because only working with the activities and the timestamps and the case IDs is somewhat limiting as well. All right, good. Another point I want to make regarding that event data is, well, typically not something that I don't think we have talked about this in the introductory session, but well, events pertain to activities, right? So events reflect the execution of an activity in a business process. We can also talk about the fact that activities themselves have a life cycle, and that you might have multiple events that reflect state transitions in that life cycle of an activity. So to some extent, what you see here is, I think, the BPMN 2.0 activity life cycle model. So you might not just see one activity pertaining to one event pertaining to a single activity. That's something that we by default assume. That's what I said here, like the default in process mining would be atomic activities with completed events. So only the completed event is observed in the data set, and you only use that event type to reflect the activity that is being completed. Or in many cases, at least especially if you have an interest in performance analysis, preferably you would like to have basically two events being registered in the data set, and then typically the started and the completed event, because then you can, of course, do a more fine granular timing analysis, right? I think this is something that you know. There also have been some people that have been working on other event types. For instance, if you see abortions, etc., some like kind of stranger event types. But in typical process mining cases, we would either work with atomic events, and then we typically assume that the event that is observed is the completed timestamp, or we work with two events per activity, and in that case, we typically have started and completed events. Okay, is that clear? Good. So where do we source that data from? Where did you source your event data from? Well, exactly, yeah. It can be anything. I listed some things that are typical. If you're lucky, you might extract data from a BPMS, but not sure whether they are so widely applied in industry. Case management is another example, or ticketing systems. Most people actually extract their process mining data from business suites like SAP, Oracle, and others. But sometimes you also, as you said, you might have a data warehousing or a business intelligence solution that by accident also tracks a lot of data that ultimately has maybe timestamps in columns, but ultimately these things might also be converted to a format that is that is convertible to an event log. So it's very flexible in terms of where you might actually source your event data. Web data is also oftentimes used, not always so easy to work with, but typically also can find or retrieve that structure of having a timestamp, mapping it to an activity, and mapping it to a particular case. So clickstream data, IoT data is also a source of data that is used more and more in process mining. It's also something that I will come back to later in this talk, right? So this is just a quick overview. Tomorrow you will see, I think, a particular focus on how to source data from SAP. So that's something that will follow tomorrow. I will not spend too much time on event sourcing, in a sense that over the past 15, 20 years of process mining research, also a lot of researchers have invested time in developing software, tools to extract data, to source data, to like load it from a CSV, load it from a database, etc., into access structure or into another type of event structure, also object-oriented structures, for instance. I will not really spend too much time on those in this particular talk. You can read a bit on it in the book chapter. So I will remain quite abstract in that sense. But tomorrow, as I said, Raphael and Julian will talk about a particular way of extracting data from SAP. This is just one slide that comes from the CSS survey that was executed, I think, last year in the run-up to the ICPM conference. I'm sorry, and there you can clearly see that like most of people applying process mining in professional services, but also elsewhere, would look at SAP and related business suite data sets that you can obtain from those tools. Of course, event log extraction is challenging, right? And this is already a quite old slide, but to some extent there are some complexities, and some of these complexities I will address them in the remainder of the talk. There is correlation, right? Sometimes you might find events in different parts of your information systems or from different information systems, and you need to bring them together under the umbrella of a case ID. But if these case IDs are not there in your different systems, of course you have a problem, right? So that's the problem that we denote as correlation. So how to make sure that events that you collect in a wide variety of systems, in a wide variety of databases, how to bring them back to the level of an event log where you assume that every event pertains to a case. That's not an easy task in some environments. There's timestamp problems. Typical example is in healthcare, for instance, where you still see a lot of manual logging or semi-manual logging, where like nurses, for instance, start logging like after they did a tour of all the patients, they start to fill out everything in the computer, and then you see like everything basically happening at the same moment in time. You have some very poor system designs where certain events are only generated when you, I don't know, submit a button, and then also all the actions that you have been doing before that are only registered with a timestamp at the moment that you submit the actual task, for instance. So yeah, there's lots of timestamp issues that you see in data if you start working with real data, right? Delayed logging, that's what I explained. Different clocks sometimes, and also sometimes just granularity problems. For some reason, the person who designed the database decided to only store the date, but not the time. Yeah, of course, then it becomes challenging, right? And then you have like, a problem that you would need to solve. Snapshots can also be a problem. So the fact that for some processes, I work, for instance, with a construction company. They do really large construction sites in Belgium. It's not only a problem that they only do a few of those a year, right? So you only have a few new construction sites of that size a year. But also these construction projects, if you look at it from the real start, so the moment that someone instructs a company to start building a larger industrial infrastructure, until the moment it is delivered, that's like sometimes a 5-year-long project. So to collect data for those processes which typically have a very long lifespan, yeah, you often look at only a part of the process for every case, and that makes it also quite challenging, because you really look at snapshots, and most process discovery algorithms that we've looked into so far, they actually assume that you have process instances that have like a start and an end, right? So where you observe the full case, and where you don't only observe like a snapshot of it. There is scoping. That's a very important question. We will come back to it, right? What is part of the analysis and what is not, right? If you source data from SAP, for instance, you have lots of choices to make. You cannot just use all the data. You need to, at some point, filter the data, select data, scope your analysis. And that's not an easy question, because it's often something that is driven by business insight. There is no general guidelines on like how to set those filters. Do you look at data for the past year, for the past quarter? Do you look at those order types and not those order types, etc.? So there are different choices that you need to make. And yeah, they basically refer to the question of like which tables to incorporate or how to scope your analysis. For that purpose, you typically need people that both understand the business very well, but also relate to like the data infrastructure, the system infrastructure, and those people are hard to find, really. That's not an easy task to have them in a company, to understand like people that have a technical knowledge about the systems, but at the same time can talk to the business people to understand like, okay, what is of your interest? Huh? Because business people can raise many questions, but to translate that to a systems and data perspective, that's not an easy task. And then finally, granularity, that's something I will also talk about, is in some environments, you collect event data, really with timestamps and case IDs and labels, but at a completely different granularity level than you would expect. We started, I think, yesterday morning to say, like, we look at business processes and we need activities, but these activities, we automatically assume that they are business meaningful. So if you then develop a model, and you look at the model, and you let anyone in the organization look at the model, the person can read the model and understand it. But some event sources are at a much more fine granular level. So you cannot just apply a process discovery algorithm on that data, because what you will see is not necessarily only spaghetti, but it's just like not comprehensible at all, because you don't have the tasks that are business or the activities that are business meaningful in your visualization. So also that is a problem that is addressed in data preprocessing, how to bring that low granular data, those events, to a level, to an abstraction level where you can work with for applying process discovery and getting business meaningful insights. So what do you need in terms of skill sets? Well, that's also something that especially Mo, and Mo has done a lot of work on this survey. So what skills do you need? Well, basically SQL. SQL skills are like, if you would need one skill to do data preprocessing, extraction, management well, it's probably SQL. That's very obvious from the question in the survey as well. So database management, possibly given the complexity of many of those enterprise suites, also some knowledge on those enterprise suites might be extremely useful. And then, especially also in research, we have often seen that many people just needed data wrangling skills, right? Regular expressions, proper usage in Excel might also already do partly or part of the process. If you can program, it's sometimes helpful, and nowadays we see that most people would, for instance, implement their pipelines in Python and don't really resort to these kind of classical business softwares that you would see. But still, there is quite a lot of manual tasks oftentimes to make sure that your data is pre-processed and ready to analyze. Storing event logs, also in the chapter we talk a bit more in this. I decided to keep it light and short, so there's also quite a lot of development in terms of the access standard. OSL is there, of course. We have some good standards. We are working within the task force and within the access working group. Eric is, for instance, one of the key members there. We are now working towards a new standard, a new access standard, or at least an updated version of it. And this is, of course, important. Main problem with these standards is that they are well thought of, they are really nice to use, they make it easy for process mining analysts to conduct analysis, but of course in source systems, these types of formats are not really supported yet, right? So that you will not source your data in access standard format, right? Maybe in the long run it might happen, but for the moment I don't think you can expect these main business suites to start logging event data in a standard that we've developed within the process mining field. Maybe at some point it will happen, but at least for now that's not yet the case. But especially for structured storage, these are things that are like really well thought of and that you definitely should use, and we hope that many tools support it, and not only support it, but also try to push the standards forward. I think that's still something that has been lacking quite a lot. So yeah, this is the overall picture. By the way, there are some very good overview papers in the field, actually quite recent overview papers. Like for instance, this paper that I cited on the bottom of the slide is actually a paper that is very comprehensive in terms of like going through all the different scientific works that have been written on data extraction, data correlation, and also abstraction of event data. This is the overview picture that they put into the paper, and well, basically, I've shortly looked into this part here, extraction. Basically, not touching too much upon it, given the scope of the presentation of tomorrow. And what we will do is look into abstraction and correlation as the main other tasks that you need to carry out as part of your event pre-processing pipeline. So those are those two tasks that you see here. And what we basically need to do is, correlate data. So that's what I explained before. We need to bring back events to a setting where you have a case ID for all these events, a joint case ID where you can have an understanding of a case in function of all these events. And then there is event abstraction, that's the other part here, where we basically look into how to work with lower level event data and try to bring it back to a level of useful analysis, let's say, right? Good. So that's event correlation and abstraction. That's what I want to talk about. Event correlation, that problem is well described. I think it's also still a very relevant problem in practice, to be honest. So I think there is still environments where event data is sourced from different systems and there is no natural way to integrate them, although that like maybe 10 years ago this was much more prominent. I think nowadays might be less and less prominent, also, especially also given the focus of many of these commercial toolings to try to automate or at least semi-automate the data extraction from main typical source systems. I think that's something that they have been focusing a lot on. So to some extent that event correlation problem is still there. So in practice, that data integration aspect and data integration patterns, I didn't introduce any slides here, but you have lots of database management, scientific literature, but also practice practical tools that kind of make you understand how to reason about data integration and how to apply patterns of data integration in order to make sure that you can achieve this. On the other hand, if you look at research, we have mainly focused on problems of, like, for instance, missing case or IDs, or how to infer a case ID from event data that has no case ID, basically, right? So those are concrete problems that fit within event correlation that might be present in practical problems, but basically in research that was a focus that some people have been taking. Here you see some papers that have been published over the past few years that have particularly addressed that problem of how to infer a common case ID for event data where this case ID was either absent or where some events were not correlated by a case ID. So you would have a case ID for some events, but not for all of them, and how to infer then the case ID for events that don't have that case ID. I will not detail all these different techniques. If you're interested, you can definitely have a look into these papers. There's different techniques, right? So there is model-based techniques, like based on Markov chains, and also the paper or the technique by Felix Manhart is also a very nice one there. You have also recent techniques, for instance, in the object-centric domain. Then I move to event abstraction. So that's we have event correlation and event abstraction. That's the second task. This is only common for those applications or for those systems where you would source your data at a level that is lower than the typical analysis that you would need to have if you show your model to business users, to experts who would need to understand the business process at a more high level of abstraction. But in the system, you would record your data at a much lower level. IoT is one such example where I will come back to. But for instance, what you see here, sometimes in some systems you have basically something like clickstream kind of data, or you see like what is being recorded in terms of inputs into the system, and you need to understand like what is the higher level business activity that is going on here. That's exactly what we mean with event abstraction. Overall, we have two approaches to apply or to conduct that event abstraction. They are supervised and unsupervised abstraction techniques, right? And the difference is pretty easy. In a supervised fashion, you expect some kind of prior knowledge to guide that abstraction process. I will explain in a second in more detail. In an unsupervised fashion, you assume that there is no prior knowledge, no expert input. You just rely on the lower level events that you capture, and by means of intelligent techniques, you try to figure out what are interesting patterns that could lead to abstracting lower level events into higher level events. So that's basically the difference that you see. Here you see a full overview. Again, the paper by Sebastian is really a nice reference work on, like, if you look into event abstraction techniques, a very recent survey. It covers almost all the techniques that are relevant in the field. So if you have an interest in this field, start there, I would say. But to bring it back to the main difference, so in the supervised learning techniques, we expect some prior knowledge, right? This can be simple prior knowledge, like for instance, just understanding a timing interval over which you should aggregate can already be sufficient. If you tell me that you record lower level events and these lower level events should be mapped, for instance, every 5 minutes or roughly every 5 minutes, this should reflect to a business activity. If you just give me that information of like the difference in granularity level in terms of time, you can already devise interesting techniques to bring these lower level events to a higher level event, right? That's a form of input that you see in supervised learning techniques. There's also manual mappings, right? Basically explicited expert knowledge that you apply to these lower event data to transform it to a higher level event or to a set of higher level events. This is typically not easily obtained, but a lot of techniques actually focus on that manual mapping, trying to extract that knowledge from experts in order to build a mapping that can be reused in order to do the mapping of these lower level events to higher level events in a structured fashion, also on future data that is being recorded. And then we have some techniques, and those are very common, that try to start from some higher level model. So some kind of normative model to which you want to map your data to. Can be in the form of a process model typically, but you at least give an indication to what level or to what kind of structure that this low-level event should be mapped to. And based on that information, you can also try to derive techniques that can do that mapping, that can establish that mapping to be applied into the full data set, for instance, right? So here you see an overview of some of the papers. I will leave it here in terms of further explanations, but there is these different techniques exist. You can apply them. I don't think many of those things are implemented in commercial toolings. Most of these things are implemented in academic environments. And then the unsupervised techniques, also there, I just stick to one slide and I will not demo any of these techniques or show them in detail. But as I said, these unsupervised learning techniques, they assume that you don't have that prior knowledge. You have no timing information, you have no model information, you have no expert knowledge, explicit expert knowledge on how this mapping can be constructed. You basically assume that the data should be telling in itself, and yeah, based on some pattern learning or pattern mining techniques, you can try to extract these mappings, basically, right? Already in 2009, Jagadish and Will worked on like coherent subsequences, trying to find patterns that make that you can identify like coherent sets of events with particular relationships amongst them in order to derive higher level events. You have the work by Christian as well, which is positioned under this umbrella. And there are many other more recent techniques that focus, for instance, on hidden Markov models, on word embedding based techniques, so leveraging state-of-the-art neural network-based techniques in order to understand patterns in that lower-level event data, which is often very complex, in order to map it to a more understandable higher level of abstraction. Okay, good. So conclusion, there is actually, if you looked at the table in the paper by Sebastian, you could see that there is actually an increasing level of interest in terms of developing event abstraction techniques. This is also, to some extent, related to the fact that more and more people start looking into sourcing data from non-process aware systems, let's say, like IoT data is something that is popping up. I will come back to it later as well. So you see that people show interest in this because process mining is also being applied more in industrial settings, for instance, where you might find that type of lower level information more often. So you see an increase in publications. Most approaches still assume some level of prior knowledge. It's not a critique, but to some extent, it's not always easy to obtain that knowledge in practical settings. So despite the fact that there is lots of research invested into developing these supervised techniques in some practical settings, these assumptions might not really hold. And yeah, typically the focus of these things are control flow only, right? So something I will come back to when I talk about IoT data later. But of course, control flow is not necessarily the only perspective, and that's actually a message that complements very well with the next session by Dirk. Yeah, related fields, you have several other works, and it's difficult to be comprehensive in this whole aspect, both from a research perspective as well as from a practical perspective, but there's other fields that relate to the topic of event abstraction. You have hierarchical process mining techniques, for instance, that try to identify sub-processes within a process. Well, to some extent, it's a different approach, but to some extent, you can also say that this is related to the task. You have people that look into process mining from a complex event processing perspective, right? So they look into complex event processing systems and try to see whether, for instance, in the streaming analytics research within process mining, there is a very strong emphasis on this. Also there you see that like abstracting lower level events to higher level events is a crucial thing to do in order to, for instance, do that online processing of data. So also there you see some activity. And then there's people who work on, for instance, human activity recognition. So trying to derive what people do from sensor information in a house, for instance. That's also an area of research where quite a lot of people in the field, in the process mining field, have been looking into. All right, good. To make it a bit more concrete and to sum up that topic of event correlation abstraction, I'd like to show you one of the data sets that we worked on in my research group that is related to learning analytics. And I want to kind of, what I explained in terms of event abstraction, so trying to bring lower level events to a higher level, meaningful level for process mining, basically, for process discovery. It's true, you might have that context where you have like one to many, so one higher level event pertains to a set of lower level events, that's definitely a case that can be made. On the other hand, in process mining datasets, in event logs, you typically also have lots of additional attributes. So also these attributes might actually be used to navigate abstraction levels and analyze data from different perspectives without the need of having like this two-layered architecture with lower level events that need to be mapped to higher level events. You can actually also use attribute data to try to get different insights into how the control flow of a process looks like, and that's something that we especially did in the context of working with learning data. Let me give you an overview. So we have worked a lot on MOOC data sets, so massive open online courses. The advantage of MOOCs compared to other types of learning data is the fact that you typically have a lot of users, so a lot of cases, right? In regular classes, in Leuven, we might have quite a lot of students, but still, you look at a couple of hundred students, that's not really a lot. If you look at MOOCs, you have data sets of a few thousands of students typically, and that's already much more attractive from a process mining perspective. If you need to work with 30 students and all different traces of how they learned or worked with a tool or worked on a MOOC, it's not so easy to generalize that behavior. Even to just apply process discovery would not be such an easy task. But in a MOOC environment, you have that kind of, that size advantage of the number of cases that you can look into. So we did that quite extensively. This is the source data. This is the source data. JSON data, very common in web environments. Actually, this the default source data there, especially for anything that is JavaScript based or whatever. So this is source data, right? And how to extract an event here, right? How many events would there be in this thing? Well, it's one. So it's not an easy task to identify what it is. Why is it not easy? Well, each event is one line in JSON, but you have nested JSON, so these things refer to objects and they are nested structures. They were not intended to be human readable at all, right? So that data structure is not human readable. It was meant to just store data reflecting real-time communication between server and browser. So it's quite cumbersome to pre-process. You have lots of redundant data that is not necessary for process mining, and it requires quite a lot of effort to basically write a kind of script that would extract the right pieces of information from such a JSON log, right? But that's actually what we did. So we tried to, based on these JSON log files, to try to derive what students did in the MOOC. That's basically something that you do by trying to get to this initial data format where you have a timestamp that's pretty easy to detect, of course, a username and an event type, and then like basically a content link, right? So a web link that refers to what page this person was on or what object this person was working with. That's what you see here. And then you try to map that, of course, because that's basically a URL. So you need to link it to something that is more meaningful. For instance, in our case, we mapped that to chapters and sections so that we understood what this event would be applied to, right? Because you can find that type of activity data in the original JSON format, but not necessarily this type of data. So that's kind of the extraction process that you need to go through to map all these referrals to the right objects and to understand then the different course objects that you have in your online environment. So that's the activity, that's what you do. But what I want to show is basically if you see this here, right, so this would be the activity that we're interested in. Right? But you can actually collect quite a lot of other features. I now restrict myself to chapter and section, but actually navigating the abstraction hierarchy can also happen by including certain additional variables, which seem additional variables here, in the activity label, right? So instead of just looking at play video, we might say like, okay, the student played the video of chapter 5, section 3, right? That might also be a regular activity name. And so that kind of navigation that you can do by expanding or reducing your activity label by including or excluding certain columns in that activity label by just applying a concatenation also allows to look at a data set in, or at least at different levels of abstraction, right? And you can ask different questions in such a learning analytics environment that can be answered by looking at different granularity level. For not every analysis, you would need to look into chapter and section information inside the activity label. You can also work with just let's say the event type itself, only the event type. Of course, then you look at a different type of model, but it's possible. You navigate the abstraction level in the data. So that's something that we did, but there's other researchers in process mining who have been working a lot on that type of data. For instance, Jorge, I mentioned him before in the HAP lab, his research lab. They're actually doing a lot of learning analytics research based on process mining, and they are actually looking at similar types of analysis techniques to try to extract visual models of how students learn, understand the impact of, for instance, dropout or performance. That's something that we did in the PhD of Galina Dieva. All right, let me check the time. So that was basically a rough sketch of data pre-processing pipelines in terms of extraction, correlation, abstraction, the three main tasks that we typically distinguish in that pre-processing pipeline. Data quality is an orthogonal problem that is present everywhere, right? So it's very important to understand what data quality in process mining is about. And my main message is basically we still lack a lot of insights there, right? Even from a research perspective, there is still a lot of things that we need to understand better. Yeah, this is a bit stupid, but yeah, this applies everywhere, but especially also in process mining. Let's have a look at a few examples. So this is work from Mo Win in Queensland, or well, in Brisbane. She has been working a lot in recent years on data quality in process mining. Some examples of problems that you might encounter, right? Distorted attribute value. So here you see a data set, an original event log with a resource, right? A resource field. Might not already be very qualitative, and that's exactly the problem. So your resource is recorded, but you actually have multiple representations of the same physical person, right? So our Andrews here is basically denoted in, let's say, at least four different ways in our data set. So what does it yield? Well, if you want to, for instance, just check a certain rule, you want to check whether our Andrews didn't do a certain task, for instance, well, you might end up with the wrong analysis, right? You might say like, no, our Andrews is not doing that activity, while actually in practice, or in the data even it is the case, but your data quality was too poor to understand. Another problem is inadvertent time travel, something that we often see in manual logging, right? So here you see a data set on the left-hand side of a hospital data set, like you have cases, people arriving, or well, reporting an accident and the hospital arrival time. But here you see that like the person arrived just after midnight, the accident happened before midnight, but in the data set, the date is messed up, right? So the date was not properly recorded. That makes that you can find quite interesting patterns, right? Quite interesting things for instance, a discovery technique to pick up. Or if you start to report performance analysis, for instance, yeah, how to work with these things, right? Will you start to average over negative throughput or sojourn times? Another problem is activity label pollution, right? So that's especially a problematic issue, right? If you would have, similarly to what I had for resource, but if you would have this at the activity level, so different strings for basically the same activity, yeah, that would also become problematic. You would get different kind of paths in your model, but they are meaningless to a person looking at the model because they are basically essentially the same activity. So also there, you need to take into account data quality. Just very simple problems, but in reality, these things occur, of course, right? So in reality, and you might think like this is simple to deal with, but on the other hand, yeah, maybe not so, right? Maybe it is not so easy to identify all these quality problems, and that's exactly what this research in process mining data quality is about. Already in the process mining manifesto from so many years ago, there was already a discussion on maturity levels of event log data, right? They identified 5 different maturity levels, going from basically manual logging, where there's no quality guarantee whatsoever, to basically things that are semantically annotated and come from a BPMS system. Well, probably most of the people are somewhere in between, and well, except for this table in the manifesto, I have not really seen people analyzing these different levels in other pieces of work. So what are the questions of interest in data quality? Well, first of all, how do we recognize data quality in event data, right? So what is it about? How do we assess data quality? How do we quantify the impact of data quality on a process mining analysis? How do we potentially improve it? So maybe repair the quality of data or repair the data so that the quality improves. And how do we make sure that, well, you don't do it once, but you try to make sure that what you do in terms of data quality improvement and analysis, that it becomes a sustained effort over time in an organization, right? So that's something that are the key questions in data quality in our perspective. Let me detail a few things, right? In terms of recognizing and assessing, and in many other fields of data science and systems analysis, etc., there is a focus on data quality, and a lot of that data quality research is all about dimensions, right? Frameworks that propose dimensions, and many companies try to then adopt these frameworks on like how to look at data quality, but it often really remains a very descriptive analysis without a lot of actionability, right? So people just describe a setting, just analyze certain of these dimensions, but what to do with it, right? How to solve it is a much more difficult question, of course. But still also in process mining, we do see that, well, this is a non-process mining quality dimension picture, but if you look at process mining already in 2011, a model like a description of what data quality could look like in process mining was put forward. There, they identified missing data, incorrect data, imprecise data, and irrelevant data as being the 4 key dimensions of data quality. That's an interesting framework. I mean, to some extent, it has value. Maybe there is a better approach to do that, to look at more like a pattern-based analysis, or how to be a bit more systematic in the analysis of these data quality problems. Maybe we should look at how these problems come about, right? And that's actually what most team investigated, how to document these data quality issues from a pattern-based perspective. And in Suryadi's work, they actually looked into imperfection patterns, where they identified 11 of these imperfection patterns that can be mapped onto an event log and that can be analyzed according to, for instance, the framework that they put out in terms of all these dimensions here, right? So this is a process mining specific data quality assessment framework, basically, that has a strong pattern-based viewpoint, right? So they try to make sure that the data quality issues that you typically observe in event logs are mapped to particular patterns. And based on like whether these patterns then occur in your data, you can try to devise rectification strategies. Maybe you need to investigate how the data was originally logged in the source system, etc., right? So this is a very interesting alternative to a quite generic way of looking at data quality in terms of different dimensions. This becomes slightly more actionable. It's still a descriptive work, but to some extent, by using that pattern-based approach, you can try to move towards how to improve data quality, how to take rectifying actions. So here you see them plotted. So these are the 11 imperfection patterns, 5 at event level, case level, and log level. I suggest that if you want to have a more in-depth look into it, that you have a look at Mo's paper. So from that perspective of data quality dimensions, I hope it still works. From that perspective of data quality dimensions, especially in Mo's team, they have also how do we go a step further, right? So how do we go from just a very descriptive analysis of data quality and a kind of dimensional analysis towards not only accurate detection, but also strategies to improve the quality of the data, repair data. And well, basically, there are a couple of things, right? So what people mainly do in data quality is looking backwards, right? And we know that in process mining, the impact of data quality is crucial, and it's known that it's important and that you need to account for it. A lot of people look back, right? What are the problems? And then we can, of course, take like initiatives to try to resolve these problems. But maybe we can also try to look ahead, right? So not only look at like where the data comes from and try to solve problems there, but also try to make sure that we have process mining techniques that can cope with data quality issues, right? That's basically a bit of the perspective of looking ahead. How do we make sure that the techniques or the models that we produce or the insights that we produce are informed by data quality, right? Because solving data quality, I can tell you, we've worked with so many banks, with so many other types of institutions. You don't just tell a bank like, the data quality is super poor, please rectify it. That's like, yeah, it's an impossible task, right? If it's people logging certain stuff in a particular way, you don't easily change that method in the way they or how they work. So that forward-looking perspective is actually quite interesting, and they have looked in a couple of different things, right? For instance, quality-informed event log generation is a very interesting perspective where, well, while producing your event log, you would keep track of data quality dimensions, right? You would, per attribute level, you can compute like certain statistics, metrics that quantify data quality. Well, let's be aware of those at the time we create our event log, and let's maybe also use that data to enhance the information that we put into that event log, so that we might use that quality level information for later analysis purposes. If you then have a field, whatever, supplier, but you know that 80% of the suppliers were missing, well, maybe it's good that you know that at the moment that you start looking at the data. So that's exactly what this research is about. It's a very simple tool, but it basically, at the time that you load your data, identifies the quality of the certain attributes that you load, and by taking that into account, you can decide to maybe not load certain attributes, or maybe to incorporate that information in the access file or in whatever log format that you like to store your event data. Another idea is quality-informed process mining, as I mentioned, right? So it's good to be storing that data or being aware at the moment that you create your event data set. It might be even more interesting to be able to use that data at the time that you apply discovery or performance analysis. That's what they do together also with Sander, part of the PhD of Kanika. So where you would basically try to annotate an event log in order to be able to tailor discovery techniques or discovery or any other type of technique to include that data quality information in the mining technique, right? So that's interesting. You have the quality-informed visual miner, right? It's I talked to Sander before the presentation. I think it's in a different package in Prom, but it exists as a different tool, and you can basically, it basically can rely on the data quality information that you encoded in the event log. For instance, to obtain better estimates of performance measures, or even in the model itself, certain data quality issues might prevent you from identifying, for instance, an end split because the data was not registered properly. Well, you might then include that information about the fact that the order of certain events is uncertain in order to derive a model that would give you the right control flow pattern, despite the fact that in the original data, the patterns were basically sequential, for instance, right? But if you encode that this sequential data, due to, for instance, timestamp issues, was not really accurate, you might encode that, and then the mining technique takes into account to still derive maybe an end pattern instead of just a sequence or whatever, because it is more reflecting well, what actually is going on in the data. All right, good. And then the final thing I want to mention is work by, amongst others, Sare, who is, well, I will come back to it later, organizing a workshop on data quality together with Mo and myself at ICPM workshop later this year. Well, she investigated basically gamification to improve the data quality of an event log, and in particular, the activity label. So what they basically set up is a whole system where users would go through a gamified environment to try to, well, rectify or consolidate activity labels, right? So that's basically what you see here. So they would start from an event log, which was poor in terms of data quality, and by going through a gameplay stage, you would basically try to come to, well, let's say a common aggregated and agreed upon set of activity labels that can be used for subsequent analysis, right? And that's also quite interesting because it really tries to tackle the problem of how do we solve or how do we repair certain quality issues which are not so easily tackled at the source or at the moment that the data is being produced. So yeah, let me wrap up that data quality part with this slide. So we have set up a workshop on data quality. at the ICPM conference, so a warm invite to, if you have ideas, research ideas, if you got inspired by some of the things that I mentioned in the past slides, and you want to talk about those or explain things to us, well, the workshop in Bolzano will hopefully be a success, because we think that, well, both for researchers but also for practitioners, it's a field where we still have to invest more time and effort to understand things better and to also identify certain problems in a better way. Good? Still with me? Yeah? Any questions? So I've prepared some more exotic pre-processing techniques. More exotic, well, it's already warm outside, so I didn't actually have to use the word exotic. More pre-processing techniques. A couple of things that we've also worked with within my research team, or we are working on right now. So let me go through it. So first of all is the topic of IoT. Then I would talk about trace clustering, which was actually one of the main topics in my own PhD. And I think it's a very relevant and interesting problem that maybe didn't receive much attention or enough attention over the last few years. And then autoencoders as a kind of advanced techniques to deal with data quality. So Internet of Things data, that's interesting. Who is looking into IoT type of data at the moment? So there is, I see an uptake within the field of people showing interest into IoT business processes. You have manufacturing, you have healthcare, very important area, logistics, smart homes as well. So there's lots of areas where you see that this type of data is becoming available and where people in our field starting to gain an interest into exploiting that data from a true process perspective, right? So yeah, the Internet of Things is there. We know that there are sensors and actuators and there are different devices collecting all kinds of information. And I will not mention, well, I mentioned it now, but I will not talk about GDPR at all. But let's assume that the data that is being collected can be analyzed, is allowed to be analyzed, and especially in manufacturing settings, etc. This is typically not really a problem. In healthcare, well, let's say that that's a slightly more difficult story. But in any case, what we've seen in research is that over the past, let's say, 5 to 10 years, but especially the last 5 years, process mining research has focused, for instance, on how do we enable mining, right, without the recording of true events in a data set, right? So how do we go from sensor measurements, basically, you can call it sensor events, but just a bunch of sensor readings that you obtain, to a process model, essentially, right? That's an important question, and a lot of people have focused actually on that particular question, right? We have an environment, we know that a process is being carried out in that environment, but we don't have the event data of what people or machines or whatever objects do in that environment. We only collect like the environmental factors or certain things that happen to objects, for instance, but basically based on measurement data, right? The temperature of whatever, a location, but not truly the actual activity that happens to that object or to that case, right? So that's something that we have focused on. We are also looking into, well, this, as I said, these IoT sensor data often can be used to try to infer process events or activities within a process, but they're often also contextualizing the environment in which the process is executed. So it's not only it's interesting to try to discover a process from IoT data. It's even more interesting to also understand that certain pieces of that IoT data might not be necessary or useful to identify events, but might be interesting to understand additional external environmental factors that can be useful for process mining analysis, but not under the format of the event. Maybe as additional attributes they can become interesting. But that's also something that we look into, right? How to contextualize existing event data by means of these IoT sensors, right? So yeah, there is lots of challenges, and I don't have solutions right now. There is a lot of people in process mining working on that abstraction, basically event abstraction problem. So going from sensor reading, sensor events to high-level meaningful process events, that's interesting, and that's something that, well, is necessary, right? But IoT data does not always relate to control flow, might also just reflect process context and not only control flow. IoT data is not always synchronized with the process, right? So typically, the way that you obtain IoT data is much more fine granular than the timing of the events or the time granularity of the events that you capture. So also there, we are typically a little bit in trouble in terms of how to store the data, how to combine the data. So that synchronization issue is a problem. Quality, not sure, I mean, like in regular process-aware information systems, data quality can already be pretty poor. Imagine that you work in a sensor environment where sensors get outlier readings, sensors are defect, whatever. You have all kinds of problems in IoT environments, also alignment of sensors, etc., that impact the quality of the data that you use. So also there, that's a big problem. And then IoT data volume, right? Typically, if you compare it to, well, in process mining, we might look at large data sets, but if you look at like typical IoT data sets, it's a few magnitudes more of data that you're looking into. So yeah, we have been studying a couple of things in our own research group, for instance, in terms of contextualizing sensor data, so not only using it for identifying events, but also trying to understand how we could use IoT sensor data as an additional contextual piece of information, so trying to bring it next to a control flow perspective. I will keep this short, but we, for instance, worked on a simulated case that was well known in the context of IoT process modeling, where they would basically look at a kind of smart distribution center example where you would have like fresh produce, for instance, arriving on pallets in a truck, and you would need to unload them, and the first decision that you would need to make is basically, are these fresh produce, or is this fresh produce still sellable, right? Is it still good enough to sell it? And this depends on a lot of things. And you have now like very smart pallets and trucks that keep track of all kinds of physical contexts, right? Temperature, shocks, movement in all kinds of directions, etc. So we have that information. It's low-level data, right? It's like temperature readings every half a second or even every second, movement data, very fine granular data. Question is like, okay, here, basically currently we do a manual inspection, right? So a big truck arrives, we take one of these pallets, we take one basket out of every pallet, we look at the whatever, apples or whatever, the fresh produce. If it's good, we keep it, and the entire truck is kept and it's being sold, right? That's basically what is decided. So it's a human process. Of course, we can try to improve on that, right? Because if we know that in certain cases, for instance, the temperature patterns were in such a way that, well, these fresh produce are not fresh enough anymore, we can try to derive that from data. But that's difficult, right? That's difficult. So that's something that we are trying to work on and trying to see how we can basically encode that information and try to, not only store that information, but then also use that information to enhance for instance, a model in terms of decision point analysis. So yeah, here you see the question. So were the transport conditions okay? We want to assess humidity, temperature. This is basically a time series type of data input that you need to analyze, typically multivariate in terms of the different types of measurements that you keep track of. And then you need to decide, the decision model is basically unknown, right? So we need to understand this. Typically what people would like to do is try to aggregate that information to the level of events, right? So if you looked at the process model here, right, we would be able to have events for each of these activities, read temperature and humidity, read pallet labels, etc. So we would have events pertaining to these activities. The question is a little bit like, can we store time series information like the information that I mentioned here, right? So this type of information, can we store it at the level of the individual process events? That's not an easy thing to do, in my opinion, because the time granularity of this time series is much more fine granular. How do we know, like, the events that are registered here in terms of when they occur might have nothing to do with the impact of the temperature on my fresh produce. It might be that the temperatures patterns over the past 1 hour were relevant, but the moment that I read the pallet labels, the temperature at that moment is completely redundant information. I don't need to know it, right? So the question becomes a bit like, how do you store that data? Of course, if you know the pattern, if I tell you, we look into the past 1 hour, okay, you know it, and you can store it in that event. But if you don't know that the last hour matters, how to store the data, right? That's a bit of the question that we try to look into. So yeah, that's still, in my opinion, an unsolved problem. What kind of patterns do you store? Do you store outliers in over a certain time period? How do we log this? How do we deal with quality issues there? It's also a big problem, missing data, sensor failures, etc., and the multitude of data. So as I mentioned, in our case, we try to simulate this model. We assume that there is just like one measurement a second, 5-hour transport with 6 sensors. For 200 cases will already lead to something like 21 million measurements, which is, doesn't look like a lot, but is still, in terms of management, not such a trivial question. And if you look at event log standards, well, XSS, you could think of ways to extend XSS to try to accommodate for these types of IoT level input data. But it's not easy, as I just explained, right? We cannot assume that every piece of IoT data that you collect from these sensors relates to process events, for instance. That's an assumption that is often made, but I think you lose information there. And on the other hand, trying to bring everything back to other types of features that you store at the event level might also not be ideal because, the granularity is very different and the patterns that you want to detect over this IoT data might not match with the event level time granularity. So that's an issue for XSS, and actually also we have analyzed OSL as well, and also there, we see some issues that, well, you basically have difficulties to log at different granularity levels. You could potentially think about storing different types of events in OSL because you could say like, okay, we create an object being an IoT device, for instance, and we track events for that IoT device. So intrinsically it would be possible, but it's still not a solved issue by switching to OSL. So yeah, IoT data is interesting in process mining. So far, many people have focused on that event abstraction ID. A lot of opportunities exist to go further and to try to extract or develop techniques, both at the storage level, but also at the discovery level, to work with that IoT data in more flexible way. So if you need some inspiration in terms of topics to work on in your research, this is definitely something that I think should gain your interest. All right. Then trace clustering. That's another topic I think where, I think it's of interest. When talking especially to practitioners, I see that there's a need for these types of techniques, but maybe also in research we haven't been focusing a lot on this. What is trace clustering, by the way? Maybe some of you might know, but in trace clustering, in event abstraction, we try to basically cluster events in a horizontal way, right? So we try to bring groups of events together to a higher level of abstraction. It's also a form of clustering to some extent, you could say, but it's horizontal. We here want to separate a log vertically, basically. So we want to create, trace groups, basically. So we see so many cases, right? And we want to make sure that we can find groups of traces of interest, groups of cases of interest, right? And that's what we do in trace clustering. So we basically start with a full event log and we try to derive sub-data sets, sub-event logs that group cases for which typically, and that was the original problem formulation, right? But maybe there are other problems that you might solve with it. But the original problem that we tried to solve was the fact that you would obtain a very inaccurate and very complex process model. And even given the very nice and interesting process discovery technique that have been proposed in the recent years, I think there is still a problem with many data sets in terms of the complexity of the model that you would obtain. So this trace clustering is interesting. People have looked into this problem, of course. If I look at it broadly, it's not a perfect categorization, but let's say broadly, you see two types of approaches, right? You can look at it from a very data-driven, and I call it here distance-based perspective. So you have your cases in your data sets. They pertain to sequences of events. You try to basically featureize these sequences and then apply a clustering technique on top of the features that you derive. So you can keep it very simple. You could say, like, I just define an activity profile. I just create a vector with all my activity labels, and I just indicate where that activity is present or how many times that activity was present in a case. I have a vector representation of all my cases. I apply k-means to it, and I get a solution, right? That's a very simple distance-based clustering solution that can work very well in some cases, right? You could also use trace attributes, for instance, on top of that. You can use more complex patterns, like, for instance, 2 grams or 3 grams, or Jagadish also suggested some very, very exotic types of patterns. You can use a lot of things to create that feature vector, and it can become a very a high-dimensional vector. But to some extent, that's interesting. We approached it from a slightly different perspective, in the sense that you can also look into a more model-driven approach to trace clustering, because every single of these clusters, groups of traces, actually, in the end, what you want to obtain are good process models that reflect that group of traces well, right? So you can also try to drive that clustering algorithm by means of the underlying models that it produces or generates, right? And that's exactly what we try to do in research in our group. Also, other people have looked into it, but the algorithms that we developed try to, for instance, optimize an underlying Petri net or an underlying process model representation in order to, basically guide the clustering by means of the underlying model. This is interesting because, to some extent, the behavioral patterns that you try to extract in the data-driven approach are, well, not always aligning well to the quality of the models, right? So it's not because you use a very fancy type of featureization technique to capture control flow patterns among the cases, that if you then apply a clustering technique to it, that you would group traces that ultimately would lead to coherent and high-quality process models. So trying to bring that process model inside a clustering algorithm from that perspective is relevant. And why is it relevant maybe for people in practice? Well, if you look at Celonis, they also come with some kind of clustering, right? Or at least what they call filtering, but to some extent I see it as clustering, because they allow you to just basically navigate through your variants by means of frequency. And they say, like, look in variant 1, and you can also select variant 1, 4, and 6, etc. But this is purely frequency driven, right? So this only looks into frequencies, and if you drag and you say, like, okay, I'm interested in the first six variants, and the model shows you something, is that a relevant part of your event log to look into? You do the same thing. You throw out behavior, basically, to understand the model in a more simpler format. But yeah, it might be much more interesting to understand that, for instance, variant 1, in terms of behavioral similarity, is much more related to 5, 6, 7, and 8. So let's look at the group of 1, 5, 6, 7, and 8 together. That would make much more sense from a behavioral perspective. But it's possible in Celonis, but it's not supported in that sense that you know which variants belong to each other in a joint analysis, for instance, right? So what I just explained you in terms of trace clustering, this can be translated to a very practical solution in a commercial environment, which could help a lot in terms of how you scrutinize an event log and how you search for different ways in which a process is being executed. Maybe your event log contains a lot of different variations of a process. Analyzing them all together might not make a lot of sense, right? You have different types of rules, different types of practices for different cases, and you might know that they are there, but you might not know them all. So these kind of data-driven techniques can actually help you to identify these subgroups of cases which deserve their own analysis, their own model discovery, their own conformance checking maybe, and that's something that you can achieve by, in our case, a more data-driven clustering approach. So that's why I think it's not only relevant for researchers, I think it's also highly relevant for people looking more at software and process mining solutions. From that perspective, I think it's relevant. What did we work on? And I will keep it short. We worked on model-driven trace clustering. We worked on multi-paradigm trace clustering. We worked on explanation techniques for these trace clusters because, of course, given that you make it data-driven, you still want to be able to explain to an expert, this is what our algorithm actually produced, and this is how you should interpret it. So we developed techniques that try to explain these trace clusters. And we also worked on expert-driven trace clustering, where you would basically not only guide the clusters by means of, for instance, the models that are created underneath or the data features that come with your traces, but also informed by certain expert knowledge, right? For instance, saying these two cases, despite the fact that they look very similar in terms of how they were executed, I still want them to be in separate clusters, right? So we retrieve that data from experts, and then we produce a trace clustering that is not only behaviorally optimal, but also tries to incorporate those expert information. Good, so let me have a quick look. So ActiveTrack is one of the algorithms that we developed. It's I would say a rather naive technique, but to some extent it still works pretty well in the sense that you just run sequentially through an event log, case by case. We typically try to order them, well, we try to group them by variant and then run through the event log. That's typically a little bit more computationally friendly. But we basically create process models and we try to assign our cases to the different clusters, but basically based on how well they fit in certain process models, right? So that's basically how we try to derive the clustering. We have improved this, or at least we have tried to make these approaches more scalable by looking into a hierarchical structure where you would first try to identify what we call super instances. So we create a clustering that is data-driven or that is steered from a data-driven perspective, for instance, based on trace similarity techniques, and then apply model-driven techniques on, well, only on the super instances. So let me maybe show that to you. So we first create an overclustering. You can say, like, for instance, you use the activity profiles or maybe something slightly more complex. You apply k-means, that's relatively scalable, goes pretty fast on most data sets. But you create, like, let's say 50 clusters or 100 clusters, something that is not really reasonable from an expert to say, like, okay, you cannot work with 100 clusters, right? So that's not really doable. But we, in our approach, we do create, let's say, 50 or 100 or 200 clusters, purely data-driven, to try to understand a bit like, okay, where are the most common sets of traces based on a simple featurization, but then based on that we select super instances. So we select one observation, one variant in each of those clusters that is most representative for that cluster. You could do it in different ways. You can do it frequency-driven. You can do it based on centrality within the cluster, like how representative is that trace with respect to all other traces. So you select your super instances, and then you apply a second clustering approach that works with these super instances only, and that's actually giving some very good results in terms of, well, here you see the algorithmic approach. I will skip this. This is not so important. It's exactly what I showed in the previous slide. But by doing so, by doing that two-stage approach, you can actually try to balance the computational performance with the, well, behavioral quality, let's say, of the created clusters. Yeah, that's what I show in this slide. So in terms of the performance and in terms of, well, both the F-score that we computed for the process models as well in terms of the runtime, we can strike a much better balance. Two more slides on this topic. Trace clustering explanations. That's what I mentioned before, right? So explainable AI is a hot topic nowadays. This was a paper I think was produced, well, the original work was I think presented at, if I recall well, the BPM conference of 2015 or 2014. So it's quite some time ago, before XAI gained any leverage, let's say. So basically what we developed is a technique that would do instance level explanation. So we would assume that there is some form of clustering, a trace cluster solution that you have, and then basically for every process instance that we have in our data set, we can derive the minimal explanation to denote why that particular trace is in that cluster and not in another cluster. So we'll be able to tell you, like, in this particular trace, right, if this control flow pattern would be different, if in this particular case B would not be followed by C, but B would be followed by E, basically this trace would go to another cluster. So we can retrieve minimal length explanations for instances in trace clusters, and these explanations, if you look at them in a grouped fashion, can actually also be used to try to holistically, at the global level, explain created trace clusters. And this is pretty interesting because it can be shown to end users in a visual way in order to show such a trace clustering solution understandably. And then finally, one more slide on this. We have also adapted the trace clustering approach to deal with expert input, so basically an adaptation of what we call classical constraint or semi-supervised clustering, where you would basically include must-link and cannot-link constraints. So what I just explained, right? So you have your traces, and an expert would say, like, okay, I look at this purchase to pay process. I know that we have different ways in which we execute a process, and I don't want to look into all these processes or process instances in a joint fashion. But please take into account that these two cases should be in the same cluster, and these two cases should be in different clusters. If you explicit that kind of knowledge, you can guide your clustering solution to a solution that is both in terms of the data perspective, well, optimal is always difficult to say in clustering, but better, but also safeguards what a business expert is looking for in terms of the solution. Because, yeah, as you know, in clustering, it's unsupervised learning, so you always have multiple solutions that could be equally relevant or good if you look at how business users might exploit that solution. So this is also pretty interesting if you look into applying these techniques in practice. All right, and then final 2-3 minutes on one of the recent project that I've been working on with a company, with Brussels Airports, so the airport in Belgium, the main airport in Belgium. We have actually a long-standing collaboration with them, and they actually work a lot with their event data. Not necessarily with process mining. They actually have lots of BI dashboards that are based on event data, but they hadn't heard about process mining. So we came to them and said, we have this nice research domain where we've been doing research for 10 years, and they showed us dashboards of their passenger flows, whatever, but it was all custom built, right? And they had like super nice dashboards collecting all kinds of statistics, throughput times, floats, visual models of how luggages and passenger flows would work, but they had never ever seen anything about process mining. So that was cool for us to start. But one of the key things that they do in order to enable these dashboards to work is basically to clean up their data, right? And that's like literally a 10-person team that only cleans data, right? The entire year, right? So that's like an incredible effort. So you cannot imagine. So we told them like maybe we can try to see whether there are some opportunities to clean that data in a way that would be a little bit more automated, right? So not people just going through cases and trying to rectify whatever timestamps, things that were not registered, etc. So we looked into, well, quite advanced techniques in the sense we looked into autoencoders, a neural network type of model, to try to automatically identify and also rectify these traces, basically, right? These process instances. So, yeah, this is what we assumed, right? So this is what I showed before. We think that these autoencoders are mainly interesting to try to rectify missing data. It's actually quite powerful to do so, right? In these airport data logs, we actually have lots of cases where events are missing. It's actually a very particular problem. That's because most of these events are machine generated, right? So these are scanners, security machines, just points in the system where a bag flows by, for instance, or where a passenger is being detected. It often goes wrong, right? Often these scans are like not registered. The system was not properly functioning, for instance. But we know for certain, or that's the patterns that these annotators actually use, right? So they know a first-level security check has to happen to every bag, right? There is no exception. So if you see a trace where this first-level security check didn't happen, you know that it needs to be in there, right? You know it might not be registered in the data, but it is there. It was executed, we are 100% sure. It's just because the logging in the system was not optimal. So yeah, that perspective is covered quite well by autoencoders, and also incorrect data. To some extent, there is still some more difficult issues with incorrect data, especially given the fact that, well, the process is quite complex. You have a very long tail of very low frequent variants. And there, of course, these autoencoders, they require quite a lot of fine-tuning to understand what is the difference between a, let's say, infrequent but correct observation versus a noisy, bad quality observation that needs to be rectified. That's still a trade-off that we are trying to find, but I still wanted to mention to you, it's not that we have a final solution. This is unpublished work. It's just experience from practice. But yeah, we have been doing this work. It's actually research that was presented by Timo Nolle and also I think Marco Komudzi and his team in Korea worked on autoencoders for anomaly detection and rectification. So we actually didn't really develop a lot of research ourselves. We applied their models, we tested out the different techniques that exist, and basically applied it also to the systems in Brussels Airport. So it was an interesting exercise. maybe just a very short intuition of how it works. Of course, I will not bother you with the exact details, but how such a neural network autoencoder works. Well, basically, you take your input data, and the idea is basically that you try to map it to a lower dimensional, well, in this case, Z, a latent representation, right? So a representation that needs to be learned, right, by tuning the weights of the neural network. But the idea is that you make that dimension of this latent representation layer much smaller, typically, than the dimension of your original input data. So you have your original input data dimension, you try to reduce it as much as possible, and then you learn the model to also reproduce the original inputs, let's say, right? That's the basic idea of an autoencoder, right? So you have an input, you throw it through a neural network, where in the middle there is some kind of layer that is much more low dimensional than the original input dimension, or the dimensionality of the input, and you try to map it to the same output, to the input that was the output, right? So this is the encoder-decoder scheme, and exactly by doing that, like shrinkage, basically, that latent representation and shrinking the dimension of the representation, you basically learn to identify, or the network learns to identify what are the main things, the main patterns, and what are the noisy things, the anomalous things. They are, of course, kicked out in the first place. So that's basically the idea behind using it for data quality detection and also rectification, because you can see that if you input a case here that is of bad data quality, it basically gets automatically corrected because your neural network will predict an output, which is basically an output that is like not the original input. It will rectify the trace and produce a trace that is different, right? And this is very flexible because you can use it for the sequence, but also for the timestamps, and also potentially for data attributes. And this makes it extremely flexible, complex but flexible. And this is exactly what was needed at Brussels Airport to understand how we could actually map that manual task to a model that would deal with the complexity of reality, basically, right? You can think of handcrafted techniques that would correct sequential problems, right? If you observe something, and you don't observe it, you just put it there and it's there. That's what they do, but yeah, it's a multi-dimensional analysis, of course. It's not only about the activity label, it's also about a good timestamp, it's also about all the other attributes that come with the events. So yeah, that's what you do in autoencoding. Yeah, that's exactly what I just explained, so I will not redo that. We applied it in Brussels Airport to quite complex models. And these are the typical models that we look into. And this is just a luggage handling system, right? So intrinsically, they have simulation models of this process that I can draw on a piece of A4, right? And then we apply process mining, and we tell them, yeah, your actual process looks like this. And then they go nuts, or they went nuts. Now they understand, but it took us 5 years to explain it to them. So yeah, that's what we do, and these autoencoders are one of the key outputs that we show to them, and they are now trying to implement this, use this structurally. It's not easy to convince them, but yeah, it's something that has been received very well within the project. All right, let me conclude. I sketched a slightly more academic perspective on data pre-processing. There is a lot more things to think about in process mining and pre-processing for process mining. There is predictive process modeling, a session that will follow on Thursday, where actually the perspective is very different, but also the data pre-processing and how to handle the event data is actually very different. I think Chiara Di Francesco Marino will talk about predictive process monitoring. Yeah, the way in which you pre-process that data for training models, evaluating models, it's a different story. So there's a lot of things to say about that. We worked on, for instance, the creation of benchmark data sets that could be used. Event log anonymization and privacy preservation is also something that actually belongs to this type of topic. I think Felix is coming later this week to talk about responsible process mining, and I think also that is a topic of his talk, but also there you see lots of researchers doing quite interesting works recently, and it's definitely also part of the data pre-processing scheme. And NLP is also something that I think people should exploit more. In other domains of data science and machine learning, text data, speech, but especially text data, image data, they are often very, very important for researchers to develop techniques for. Also within process mining, you see that there's actually a lot of textual data that we barely use, or that we consider out of scope of a typical process mining project. But I think there is a lot more effort that can be done to try to include textual data. For instance, also in function of data quality improvements, you have lots of information that is basically coded in text format in organizations that could be used to try to derive rectification patterns, for instance, for your event data. So conclusion, more research required. If you need ideas, talk to me. I think I can definitely give you ideas. 80 to 85% of process mining project of the effort in process mining project is spent on data pre-processing. But in research, I think 98% of research is actually just assuming that everything is fine, right? Which might not be ideal. So we need more research, but it also requires to. It's not an easy task. If it would be easy, we would already be doing it, right? So that's unquestionable. But to some extent, it requires us to think about, and also to collaborate with people in practice to some extent, but try to think at a level of problems that are sufficiently general. So not only like solving a data quality problem for one data set, but trying to solve it for multiple systems, multiple problems, and that requires a good formulation of problems. Okay. Good. I'll end here. Thank you very much for your attention. I hope it was interesting. So I see that there is minus 1 minute left for questions. So
yes, and I propose we take the questions into the coffee break. Otherwise, we'll start the last session late. So sorry about that, Jochen, but
my problem.
Thanks anyway.
Thank you very much.